Loud alarm signals sound throughout the nervous system whenever we are in danger of falling or stumbling. But weightlessness is not such an unearthly experience. We become weightless for a short while in a dive, on a roller coaster, or in an elevator. But if we remove the support by cutting the cable, we produce the exact feeling of weightlessness in space. It will take iron nerves waiting for the impact that never comes. We can only hope that man in space will eventually get used to this feeling of falling constantly. Without weight, our notions of up and down no longer exist. Man will probably have trouble orienting himself. Confusion such as this is likely to produce nausea. Some people may become victims of a serious form of space sickness. Weightless man in space must learn to guide himself only with his eyes. Beginners can combat dizziness by fixing their eyes upon one single object. The spaceman must learn to move with utmost caution. His muscles are adjusted to normal earthbound gravity. In space, any casual action will be violently magnified. He must coordinate himself under an entirely new set of rules. He can hardly avoid spinning constantly. When he crouches into a compact mass, he will spin faster. If he spreads his arms and legs, the spinning will slow down. After considerable practice, man will be able to master the art of swimming through the air within the rocket ship. For the beginner, a web of ropes might be provided. He must learn that slow, relaxed, careful movements are essential. After his first few encounters with the problems of weightlessness, he will no doubt try to normalize his life. Even the air he breathes will be weightless. Natural circulation of air does not exist, and there is danger of suffocating in one's own exhalations. Air must never be allowed to become stagnant in a spaceship. Circulation must be maintained by constant ventilation. Since all objects are also without weight in a coasting rocket ship, they must be safely secured by bolts and clamps. For handling large, bulky objects, man will have to anchor himself in some fashion. But as it takes force to overcome the object's inertia and set it in motion, it takes equally as much force to stop it once it is moving. On Earth, we are not exposed to dangers from space owing to the protective layer of our atmosphere. But up there, even the hull of the ship would not shield man against the possible hazards of the mysterious cosmic rays. These tiny bullets from the infinity of space will continually penetrate everything. They may prove to be harmful to man. The most energetic of these atomic rays might feel like stings as they shoot through the body. However, there are other bullets in space that may be of still greater concern. Meteorites. These marauders of space travel at speeds up to 150,000 miles per hour. But if one should puncture the walls of the ship, our air supply would rapidly escape through the opening into the vacuum of outer space. Without protection, man could last not more than 15 seconds before losing consciousness. Also, in the intense radiation of the sun, he would soon broil on the one side and freeze on the other. In the void of space, he will have to wear a space suit. This specially designed outfit must be a flexible, airtight unit carrying sufficient oxygen. Featuring built-in all-purpose equipment, it will afford protection and maneuverability outside the ship. Propulsion will be by means of a small portable rocket unit. With proper manipulation of this jet device, even the most subtle movements can be made.
Action, reaction.
Dining under conditions of weightlessness will present new and surprising problems. Liquids will be particularly annoying. They will not pour. They must be transferred by titration tubes. This tube will contain the liquid until it is forced into the desired location. Unless liquids are kept in leak-proof containers, they will escape and float in ball shapes around the cabin, finally coating all surfaces with a wet film. Plastic bottles will be used so that liquids can be squeezed out. Food will be cooked in closed containers by radio frequency short wave. Space etiquette will call for the extensive use of sugar tongs. Man can overindulge in space, but he will never be overweight. To relieve the inevitable tensions of space travel, we must provide suitable recreation. A game of three-dimensional pool could be particularly relaxing. Sleeping will be a new and unique experience. A space traveler will not need a pillow or mattress. His bed will consist of a net enclosure to prevent drifting in his sleep. How will man's subconscious mind react to his first experiences with space travel? Will he not suddenly be aware of his precarious situation, trapped in a tiny metal box, floating through the incomprehensible nothingness of space? We do not know. We must plan intelligently if these pioneers of space are to survive and return to Earth safely. The conquest of space will depend to a great degree on the research and findings of this important new field of science, space medicine.
To the engineer, spaceflight poses two problems. The first is, of course, to build a rocket ship. The second, and no less important, is to prepare and train the men who are to fly the future rocket ships and to provide suitable working conditions that will enable them to survive in space. To help show you what is being done to solve these problems, we have called upon one of the foremost exponents of space travel, Dr. Werner von Braun, who is at present the chief of the Guided Missile Division of the Army's Rocket Center at Redstone Arsenal. He was also overall director of the development of the original V-2 rocket.
The training methods for future space flight and the special equipment needed for survival are much like those of present high-altitude flying. And the experiments we are making today are helping us to solve the more complex problems to come. Take the present-day pressurized flying suit, for example. It has been designed for use at extremely high altitudes and is a forerunner of the suits we will wear when we make that trip to the moon. To give you an idea of how engineers and medical men are working hand in hand, here are a few examples of the research that's being conducted at this time. This pressure suit is being worn in a test chamber where the air pressure can be dropped suddenly. Notice that the water boils at this low pressure, even though it is only at normal body temperature. Blood would do the same without the protection of the suit. In other tests, without the suit, where the drop in air pressure is less severe, we see that the body still reacts violently to a sudden decrease in pressure. Lieutenant Colonel John P. Stapp of the United States Air Force has subjected himself to the tremendous forces of a rocket sled that reaches a speed of over 632 miles per hour. The sled stops so quickly that Colonel Stapp's body becomes 35 times heavier than normal. From these tests, we have learned that man can take much greater acceleration forces than crew members of a rocket ship will undergo on a takeoff. Today's aircraft are so fast and so complicated that it has already become routine to train the crews on the ground without risking lives or equipment. This is done with a device called a flight simulator. Here the crews experience all the sensations of an extended flight. The crews of future rocket ships will train much the same way. We will use a simulator on a centrifuge and employ an astrosphere to train the celestial navigators for our coming space flights. Now here's a model of my design for a 4-stage orbital rocket ship. Compared to the unmanned instrument rocket, it is quite large. But the overall size and weight of the rocket is mainly determined by the 11 tons weight of this top section. This weight dictates the amount of fuel and the numbers of motors needed to produce enough power to equalize the gravitational pull of the Earth. The payload in the top section will consist of 10 crew members plus equipment. Notice the wings, small rocket motor, and landing gears. This is a section that must ultimately return the men to the Earth safely. To produce the energy needed to hurl this stage into the orbit, we need these 3 additional rocket-powered sections. Here we have a cutaway drawing of our rocket showing the location of the fuel and the motors of each section. The first stage